Hello CS260. This is going to be your orientation video, and one thing that we're also going to cover after we go through the class plans and assignments is pointers, which is kind of one of the main issues that most people have when they're coming into CS260 is kind of what is a pointer, how does it work, and what is a double pointer, triple pointer. It could go on from there. So we'll discuss a little bit about pointers after we do a little on class orientation. So let's go ahead and begin with what you're going to be seeing this quarter for CS260, which is going to start in your modules. And you're going to have, there's videos here that are listed. Done by the author, and I also co-teach this course with another instructor, Tim O'Brien, so you might see some videos from her, but the videos I'm going to be creating will always be embedded in your homework for that particular week. So you'll see in each module, you'll see a video from me, module 1, and then of course chapter 4 module vectors. We'll be covering vectors here, and then the last one other thing that we're going to be doing is we're going to be creating a linked list together, and then we're going to template it, and that's something that you can use in your project. And one of the last things that we'll be covering is essentially working with binary trees. We're going to create a binary tree together and template it also, which you can use for your final portion of your project. So let's look at essentially what is going to be expected of you this quarter. You can do that by going to the assignments tab, and what you'll see is a breakdown of your course components. You have 2 exams that you're going to complete, and that's going to be worth 25% of your total grade. There is an extra credit module that you can have, and then you have your quizzes that is going to be worth 15% of your grade. I believe I've got them set so you can take them twice, and it'll keep your highest score for your quizzes. And then of course you have your final project, which is going to be worth 40%, and this is a pretty significant component of your course. And then you also have your homework assignments. The homework assignments will help you get some knowledge that's needed for your final project. Now let's talk about completing assignments and turning them in. Essentially, I will score your assignment based on completion. If you get a full score with no comments, that's good news. Nothing for me, it means that you're on track and you're doing well, and you get a full score. If you get less than a full score, I will give you a comment in your homework assignment submission area on what you would need to do to revise your submission, and then you can turn it back in for full points. Now, since I allow resubmissions throughout the course, one thing about due dates is they are soft due dates because you can resubmit your assignments, but that doesn't mean that you should be doing things late. Often what will happen is students will procrastinate to the end of the quarter and complete work that is substandard and receive like a 0, or I tend to try to do the pass-fail type thing because I'd rather you guys get it and get full points. I will do somewhere in between, depending on are you on the right track, are you progressing towards completion of the assignment. So due dates, yes, they are important. You don't want to get behind, because if you do turn these in towards the end of the quarter, you're not going to get the chance to resubmit them. So in that case, get them done in a timely manner. That way you can revise your code and resubmit them for full points. Now, as far as your phases are concerned, I will allow resubmissions for phase 1, 2, and 3. You will have to build a PowerPoint for your final that you'll turn in. I believe we may want to do. Well, we'll just see when we get closer to that. Go ahead and just create a PowerPoint based on what you would present, and then turn that in. Phase 4, since it's basically towards the end of the quarter. If you don't turn it in, I believe by a cutoff date, I might revise that number depending on the quarter. I believe June 15th is right around where you will need to turn it in. And phase 4, you will not be able to resubmit for 4 more points. But phase 1, phase 2, phase 3, you can resubmit if you have problems with that. You got your quizzes, take twice, but if you take it once and get a full score, I don't believe that you would need to take it again. Okay, so that's kind of the class plans and assignments. But another aspect of this course is the ability to set up a Zoom meeting with me to get help with your code. Now, that's something that you're going to have to make sure that you take your project that you created, your project file, such as one that you created in Visual Studio, and you're going to want to zip up the folder of your project. You're going to send it to zip, send it to me, and set up a Zoom meeting. If it's something simple that I can just kind of look at and tell you what you've got going on, what your problem is, I'll probably just email, message back. But sometimes, it's nice to get some one-on-one instruction from me. Also, we have a tutor that's going to be available to you that you can take advantage of, where you can do a drop-in on Zoom sessions. He's pretty good. And I will be sending that information out separately. So let's get into the main issue that students have, which is pointers. And I like to start out really simple, because when you get into like pointers to pointers, double pointers, or pointers to pointers to pointers, triple pointers, basically you start getting to the point where your eyes just kind of go blurry or cross-eyed, and you kind of check out a little bit. So when you're thinking about a pointer, it really comes down to 3 aspects, or 3 sides of a pointer that I like to call it. And I'm going to attempt to kind of draw here and give you kind of a diagram. So, but I'm going to also, as the diagram progresses, we will be writing code. And the data type of the pointer is important. If you're going to have a pointer that points to integers or an integer array, you're going to want an integer pointer. So you would declare the data type that the pointer is going to point to. But one thing to note is if you have, let's say, a double pointer, and that means that this pointer is going to point to some kind of a variable that is a double. It could be a user-defined object, such as if you have a customer object and you want a pointer to that customer. Since we don't have it defined, so the data type is important on what your pointer, the type of data that your pointer is going to point to. However, one thing to note is that pointers are always 4 bytes. Even though you know that a double is 8 bytes, the pointer does not need 8 bytes to hold the address of a number that is a double data type. Even if it's a user-defined type, let's say that a customer is 100 bytes, that means that the pointer is always going to be 4 bytes. So essentially a pointer is a variable that is on the stack, and what you're doing is you're creating a pointer on the stack that's going to point to memory on the heap. Now the stack is the automatic memory that comes with your application that you don't have to ask from the operating system, and that's why we call them automatic variables. So when you create a number or a variable such as that, which is just a regular number, it's an automatic variable. We call it automatic is because it's automatically coming from the stack, which is memory that comes with your application, that you do not need to say, hey operating system, I need some memory, give it to me. It's automatically associated to your application, and when your application stops, then the memory that it was using in the stack is freed up for other processes. So often what you'll use a pointer for is to create memory, dynamic memory, and ask for memory from the operating system that'll give it to you from the heap, which essentially the heap is just the rest of your memory, everything else. It's the memory that is not the stack, or the memory that your application already has privileges for. So there's three sides to a pointer. There is essentially the address that the pointer is pointing to, and the address of the pointer itself, and then of course the value of the pointer, or the address that of the variable that the pointer is pointing to. So let's kind of do a little diagram here. I'm going to say that this is going to be, I'm going to try to do an asterisk here. This is going to be the pointer. We'll call it PTR. And you can kind of think of it as a box, essentially. And what it is it's it's going to have an address here, and basically the address is, a number that represents, where your pointer is located on the stack, and then it's going to have another number that represents what the memory that it's pointing to. So the memory that it's pointing to could be something as simple as a number. This would be a num, and not very good a num. I'm going to be getting a tablet here pretty soon that I can be writing on, so that this is a little bit better. But a regular automatic variable on the stack, let's say that we want to point to this value, or this variable that has the address 2, and it contains the value 4. Now this addressing, below would be the address. This would be the address of the pointer. This would be the address that the pointer points to, which is this number right here. And this would be the value of what the pointer points to. So the first side of the pointer is the pointer's address itself. The second side of a pointer is what it points to. And then the third side of a pointer is the value of what it points to. And literally, no matter how complicated you get with pointers, it always comes down to those three components. So when you start breaking down double pointers, triple pointers, whatever, it really comes down to just this. But what a double pointer is just a pointer that points to a pointer. And I'm going to actually give you an example of a double pointer, which is going to be a 2D dynamic array. But let's get back into code and play around with this. So remember the three sides of a pointer: the address of the pointer, the address of what the pointer points to, and then the value of what the pointer points to. And that's always, it's never more complicated than that. It's just a matter of your syntax and semantics working with these pointers, depending on what kind of pointer it is. Is it a pointer in a template? Is it a pointer to a user-defined data type? It always comes down to these three aspects. So let's kind of give an example of this in code, and we will work with a pointer. So this is going to be our pointer. That's going to be, let's say it's at address 10. Now remember, these addresses I'm just making up. This is done by the application. Addresses are implicitly given, especially when you're working with the stack. And when you ask for memory from the operating system, you're going to get an address back that represents the first byte of that memory that from the heap that your process is given privilege over. So this is going to be address 2. And at address 10, we have a pointer that's going to point to address 2. So what we'll do here is we will give the value, and I believe in this little thing we're given the value of a number as 4. Okay, and then what we do is we're going to set the pointer to point to that number. And what you'll do is, since you're working with what the value or what the pointer holds, it's just like saying a number equals 4. That's going to be go to address 2 and put the value 4. When we're working with a pointer, we don't do any kind of asterisk or weird syntax to put the value of what the pointer points to in. It's just going to be the same type of idea. We just say pointer is equal to. That's directly, this is the syntax that directly refers to what is stored in this position. So we are going to then make the pointer point to the address of a num. Now this is when you do get some of the weird syntax. This is the third side of a pointer, and that is or the second side, what a pointer points to. So we're going to set the pointer to point to the address of the number, and you use actually the ampersand for that. So what this does is it actually grabs the address on the stack of where the number is stored, and it assigns it to store in the pointer's value. Just like we're saying a num is equal to 4, we're saying that the address of a num is going to be stored in the pointer. So that's why you don't see any weird like asterisk or something. People will start trying to, just to make it work, they'll start playing around with the syntax and semantics. So this address, which we're going to get from the stack, is going to be that value 2 here. Really, actually, it's numbers and bytes. So if you got gigabytes, the address could be 22,400 or something like that. I'm just using simple numbers to give you, you know, a fairly simple example. So what we've done is with this line, line 10, is we've actually created this link. We've now assigned the address of the number to the value that the pointer stores, and now that pointer points to a number. So we can use it to output the number, and this is when you get one of those weird syntax semantic things. This is where you actually say asterisk pointer, because what this actually is it's not, when you're using the asterisk here, it's not like using the asterisk over here. It's a totally separate thing, and this is called dereferencing. So what you're doing is you're saying, I want you to output the value of what the pointer points to. So the value of what the pointer points to, we dereference it. That means that I want you to go to where the pointer points to and then output the value, and that's this guy right here. So when you dereference a pointer, so the first side is the pointer's address, the second side is what the pointer points to, and the third side of a pointer is the value of what the pointer points to. And that's what you're doing here when you dereference it. You're saying, hey, give me the value of what the pointer points to. So you can then output what that pointer. Now, since I'm using Windows here, I'm going to put a simple little system pause in here. If you're using like Linux or Mac or something, you probably wouldn't need that. So we're just going to output here, and we're going to verify that this dereferences the pointer and outputs 4. Okay, now there's our 4 output. I'm going to put an inline in there just to make it kind of a little bit better. Output. Oh, wrong place. Control Z is your friend. Okay. There we go. So we have our 4 output, and now you can use that third side of the value of what the pointer points to actually manipulate the value inside of the variable that your pointer points to. So we can actually do this. We can say, okay, let's go dereference the pointer and assign it equal to the value 5. So what we've done is we said go to what the pointer points to and put 5 in here. So then when we output a number, instead of 4, it's going to have 5 in it. So we're actually using the pointer to reference the number. So when I output a num, I'm going to get the value 5. And if I output dereferencing the pointer, I'm going to get the value 5, because we've gone to the memory on the stack that represents that number and changed the value to 5 instead of 4. Okay, so we got our 4, 5, 5, 5. Okay. Now, one thing that you can do just to kind of check on things is you can output those 3 sides, and what you can do is you can do a cout, essentially. the pointer. That is going to be the address of the pointer. Then you can see out what the pointer points to, which is going to be the pointer. So this is the first side of the pointer, second side of the pointer. So the first side, remember, is this guy, the address of the pointer. That's why we're using the ampersand right there. That's outputting the address of the pointer. The second side is what the pointer holds. And then the third side, of course, is the value of what the pointer points to. Now, that's not going to be anything because we're not linking the pointer to a variable until we hit this position right here. So essentially, what we're going to have for outputs here will be the address of the pointer, what the pointer points to, which actually you should be setting pointers to point nowhere when you declare them. That's called initializing a pointer properly. So that should be output as 0. Essentially, you're saying this pointer goes nowhere. It points to nothing. And then we output the value of what the pointer points to, which we might get an error here or get some gobbledygook. We'll see. Yep, an error. Essentially, since the pointer points to nowhere, when you dereference it, you try to go and output the value of what the pointer points to, well, it points nowhere, so it doesn't work. So what you would have to do then is you would have to take this code, and we would actually start seeing this coming together. Now that I've made the link, the pointer actually points to something that exists, which is the value 4. And we'll take this out, and I'm going to go ahead and comment that out. Now what we've done here is we said that the pointer points to the address of a number. So when we output pointer, it's going to be printing the address of a number. So what we can do to verify that is output the address of a number. And what you'll find is that when I output what the pointer points to, the second side, that's this guy right here, it's going to be the same output as the address of the number. So this is what we're referring to when we have no weird syntax in front of the pointer. We're referring to the second side, what the pointer holds or what it points to. When we put the ampersand, we're referring to the address of the pointer. That's this guy right here. When we put the asterisk, we're referring to where the value of what the pointer points to, and that's this guy right here. So this output, the address of a number, and what the pointer holds is going to be the same thing. Okay, so we see, and these addresses are in hex. If you really want the binary number or the decimal number, you can put this in your calculator, your scientific calculator, and look at, you know, the actual. You can go into programmer and choose, let's see here, hex, and we would put in AC4 for the first one. And that's the decimal number of 11,532,996. Well, this computer has gigabytes of RAM, so that's the actual byte number in RAM of what it is. It's a physical thing. So that's why I kind of use simple numbers. So you look here, though, we are outputting the address of the pointer, which, let me get this going here. Let's see. Okay, the address of the pointer, side 1, right here. Let's bring up that output if I can find where it is. Right there. Okay, there we go. So the address of the pointer is this number, and then we output what the pointer is holding, which the pointer is holding the address of a number, which is going to be this number, and then what the value that it holds, and then of course the address of a number. Now you see here that this value is the same as here. So basically it's just showing that what the pointer is holding is the address of a number. Okay, and literally this is as complex as pointers. Well, when we start talking about double pointers, it gets more complex, but not really, because it always boils down to these three sides of a pointer. It's, you know, no matter what, this is as hard as pointers should be, other than untangling the syntax and semantics of working with a pointer. So I'm going to give you an example of a two-dimensional dynamic array. Now, there's some other videos in your shell that'll show you about two-dimensional arrays, but I'm going to show you what a double pointer is, just to kind of get beyond the, you know, when you start talking about double pointers, of course, people just start checking out. So it's not as difficult as you would think, is because when we're working with a pointer, mostly what we're doing is we're referencing memory. Now, when you refer to an array, and we're going to switch gears here a little bit, and I'm going to start talking about, instead of simple data types on the stack, I'm going to start talking about arrays on the stack. So if we create an array, and your normal way of doing an array is to use the the brace or the brackets here, and you know, we're going to create a 3-item array. Now this is actually an array that is on the stack, but would you know that this guy right here is a pointer? Yes, it is. You just don't see it. And so this is what's called a left-hand pointer, and this is called a right-hand pointer. And that's why you'll see some weird errors like L value, R value, but they're synonymous. I can actually take pointer and assign it to IArray, and now I can use pointer to assign values to the variable or the memory that's on the stack. So I can say here that pointer of 0 is equal to 1, and then if I do a cout IArray, of 0, we're going to get the value 1. And you know, I bet you you may not have known that arrays themselves on the stack are pointers. They're just sneaky. They've actually added this code. It used to be that you had to use pointers for all arrays. You didn't have this nice little subscript, you know, until they developed it a long time ago. So they just to make it easier to work with arrays instead of working with what's called pointer arithmetic. You would probably want to study that a little bit. It's kind of an interesting thing. Maybe we'll cover it here shortly. In fact, I'll put a little note here that we need to talk about pointer arithmetic. I probably spelled that incorrectly, but whatever. Okay, so this will actually output the value 1. Let's make it a little bit, you know, let's go -99 here. Okay. Okay, so you know, kind of interesting here that we actually assign IArray. Let's go ahead and kind of delve into this with a diagram. And what I'm going to do is I'm going to make this simple. No, that's probably pretty good. Okay, so let's look at a diagram. I'm going to try to do a better job of drawing here if I can. Maybe if I use my right arm. Okay, so let's go ahead and come up with a new screen here. All right, so we've got two pointers that we're working with. One is called IArray and one is called pointer, or PTR. And those are both pointers. So here's going to be our first one. This is going to be a pointer. Try to do an asterisk. And this is going to be IArray. Yep, I'm getting a tablet. Okay, that's IRA evidently, and then we're going to have another guy here, and this is going to be the pointer. Okay, so think of it as a box 2. It's going to have an automatically assigned address here, and this guy is going to have an automatically assigned address here also, and these are both going to be on the stack. They're going to be 4 bytes on the stack, and when this one's created, it's already created with memory on the stack. And what it is let's say that it's going to point to location 2, and it's going to be an array, and this is what's called a contiguous array, meaning that it's a numerical order, so byte-wise. So essentially, you're going to have three memory locations, and let's say that this starts with address 2. That means it's going to be from address 2, it's going to take up 4 bytes for that first location. And so 4 bytes here to this one, it's going to be 2 plus 4, which is going to be 6, address 6. And then we're going to have another address that's going to be 4 bytes more, and that's going to be 6 plus 4, which is going to be 10. Okay, so this is called contiguous memory, and when I say IRA of 0, or pointer 0 is equal to negative 99, what I'm doing is I'm talking about this guy. Okay, so an array pointer is going to have its own address, and it's going to contain the first byte, the first byte of this contiguous array that's all together. It only needs the first byte for this array because it knows that everything after it is just 4 bytes more. And that's why we call it contiguous. It's kind of like the contiguous lower, 50 states or 40 states, they're all together. It's because it's in order. So the pointer only needs to have one value that it holds, which is the address of the first byte in this 4 times 3, 12 byte array. So when I say here in this line that pointer equals to IArray, what I've done is I say, okay, we'll take the address of IArray, which is 2, and now this guy points here. So they're the same thing. Literally, they're the same thing. So that's how you work with pointers. Now, when you're dealing with dynamic memory, you're going to be working with a pointer that's going to be on the stack, but you're going to be asking the operating system for this memory here. So let's not worry about memory on the stack. Let's just talk about now memory on off the heap. So we're gonna get away from this type of syntax because we want dynamic memory. The problem with this memory is this has to be a constant. It has to know before compile time or before runtime how much memory this is going to take on the stack. We want the ability to create memory on the fly during runtime, during when the program is actually running. And that way we can determine how much memory that we need depending on, what the program is working with. If it knows, consider, let's say that this program needs to read in a book, a whole book, but essentially it doesn't know how many pages each book has. So what we could do is we could look at how many pages the book has and then create enough memory for that particular book that we're reading in, and then we read in another book that's going to have a different amount of pages. So that's the idea of dynamic memory is when your program can decide how much memory it needs and then create that memory. The problem with this is this line 7 is, let's say that we only use 2 slots. That means we're wasting 8 bytes of memory. And when we're dealing with programs that use megabytes and gigabytes, that's important. We want to be efficient. So we only want to use the memory that we need, and we look for how much memory we need, and then we ask the operating system to give us that memory from the heap. So essentially what we do then is we use a pointer, and we no longer use the memory or the syntax with the subscript. We now are going to use some different syntax. And what I'm going to do is I'm going to say, well, okay, I want this pointer to point to the first byte of a new block of integers, of 3 integers. So basically I'm saying, okay, operating system, I need 12 bytes. Store the first block of that memory and point, or the first byte of that memory and pointer, and therefore I can then use this pointer to reference those 3 integers that I just asked for. And this is what actually does it. Now other, old school stuff would use malloc or memory allocate, some other ways, but we're working with C++, so we use the variable new. And this also works for user-defined data types. If you want a customer, so you would do, if you had a customer object, you would create a customer object and you would say, I want a new set of customers, 3 of them. Since we don't have a customer object defined here, we can't actually do this, but this actually gives us our memory. Now the problem here with the heap is, I don't know if you've ever heard of the term called memory leak, but a memory leak is when an application basically fails to free up the memory it's asked for from the operating system, and that memory is not usable by any other process when the application is done. I don't know if you've ever had one of your browsers go wild and you do a Control-Alt-Delete and you see Firefox just using up memory, adding more memory and adding more memory until all your memory is used up. And it doesn't free it, and you have to force stop it, and then you've got issues because then you have to restart your computer to free that memory up, because Firefox or the process that didn't free up that memory, it still has privileges from the operating system over that memory, which means that any other process does not have access to that memory that has been leaked. So you need to actually, when you're done with every new statement, just get in the habit of just always deleting that memory. Okay, so the reason why we use this syntax is because pointer, the variable pointer, is the value of what is stored in this integer array, which is going to be that first block of memory here, address 2. So the operating system is going to give us this memory off the heap now, and a pointer is going to store that value 2, and it's going to point to these integers that we have available, and we can actually use them. And then when we say delete pointer, we tell the operating system, okay, we're done with that block of memory, or that contiguous block of memory. And the operating system knows that that pointer pointed to, or basically C++, it's all implicit. It knows that when we say free address 2, to free it all up. So essentially, it's important that you delete memory that you've created. So we send, with the delete command, we send it the address that pointer points to, and then it knows to free up that memory from the heap for other processes to use. And we can use this pointer now. We would just use normally. We could use subscript here. Now notice that this is called the R side, or the right side of the pointer. And we can set values to it. And let's say that we put in the address 1, the value, we got 2. So that would be an address 1, 2. We can use those 3 integers with our subscript. We could also use it on this would be the right side, using, or an R value. We can use it on the left side with an L value, and that means that we can say, okay, pointer, go to what you point to and set it equal to 3. Well, this would then set, okay, since this pointer is pointing to this guy right here, it would then assign this area to 3. So this negative 99 would go away, and that would become a 3. My horrible attempt. But the next thing that we could do is what's called pointer arithmetic, and I could say, okay, pointer plus plus, it goes up 4 bytes. Pointer plus plus, it goes up another 4 bytes. So that means that now pointer is going to contain the value 10. This is called pointer arithmetic. So this is the way that you work with arrays on the left-hand side. So pointer initially pointed to this block of 4 bytes. When I did a pointer plus plus, I told it to point to this block of 4 bytes. That's what this first plus plus is. When I did another pointer plus plus, it points to the last block of 4 bytes. So if I were to now assign pointer equal to 100, I can do a cout of pointer, go to the third value, and that's going to output, I got to dereference that. Okay, this line says go to what the pointer points to, the third side of a pointer, assign it to 100. So we've just set this is equal to 100. A horrible 100 is coming. Here we go. Here's our 100. And then we can output on the right side of the pointer and get 100. And then we can also output using the left side. Okay, so we should get two outputs here, 100 and 100. Well, looks like I got an error. I'm going to go ahead and pause the video, fix it, and come back very shortly. Okay, so yeah, I was being kind of silly here. The problem was this line of code right here, where I'll put in pointer of 2. Since we reset the initial pointer to the location of 10, or basically we've reset, we did the pointer arithmetic, and the initial pointer now points to this guy. Pointer of 2 no longer exists because that would be going out here and here. So I would actually have to output pointer of 0 here. That's kind of interesting when you're going between left and right side. I still make those mistakes. So essentially, basically the program said, hey, you don't have any access over this memory because pointer is referencing this guy right here. There is no pointer of 1 or pointer of 2. There is only pointer of 0. So now we should get the proper 100, 100. Oh, I got a breakpoint. So let's go ahead and do a continue here. Looks like we still got issues. Oh, there's our 100, 100. Okay, and the reason why we have an error is because I deleted the pointer. I would have to actually do a pointer minus minus, pointer minus minus to get it back to the initial place that the pointer pointed to. And what you could do is you could actually use another pointer to hold the starting point of your array before you work with pointer arithmetic. So what we could do is we could do something like this: integer star p, and this would be just a temporary pointer. And what we would do is we would say p equals pointer. Then we do our pointer arithmetic, and we wouldn't need to do this anymore. We could just delete p. Yeah, it gets complicated when you're working with left and right side, but after a while it just kind of makes sense, and you kind of get the idea, because I mean, once you know that the pointers always come down to those 3 sides that I've discussed, you're really on your way to mastering pointers. They're no longer a mystery to me. They were when I was first learning to program, and it took me, it actually took me a couple of years to get really comfortable with them. And now, you got languages such as Java and C# where everything is a pointer. You just don't see it. They hide it real well. So let's look into this this thing that is called a double pointer. And it's just like working with a single array. But what changes is to have a pointer to a pointer, you deal with what's called double pointers. So now this first field will point to, we actually need probably a new diagram. So let's see how well I do. Let's say that this is going to be our first initial pointer, but it's now going to be a double pointer because we're going to be using, we're going to be doing a multi-dimensional array. And what a double pointer means is that this pointer points to another pointer. And the reason why we need that is for 2 dimensions, a 2-dimensional array. Because your first dimension is now just like your single dimension over here, where this pointer points to 3 integers. If you're going to have multi-dimensions, like let's say a 3 by 3 array, you're going to then now have pointers here and here. So now this pointer points to an array of pointers that are contiguous on the heap. And they're going to be size 4, so you got to actually say int star when you do a new. And then each of these is going to point to a set of 3 actual integers. And then you have your 3 by 3 array. And that's how you do multi-dimensions. And I'm definitely going to be getting a tablet soon. Graphics tablet or something. So the next videos will be improved when we deal with addressing and pointers and whatnot. So this is what kind of a double pointer is you got a pointer that points to an array of pointers, and each of these pointers point to the actual 3 integers. And you know, a 3 by 3 array is 9 items. Well, you know, this is 9. This is 3 times 3. That's 9 actual integers. So you're actually dealing with 4 bytes here, another 4 by 3 bytes. That's 12 bytes. So 14, 15, 16, 17 bytes just to hold the information needed for your 3 by 3 array. So 17 bytes of pointers. And you know, if you were doing a double, it would still be 17 bytes here. It would still be the 12 plus 4. It's not 17. It's 18. The 12 plus 4 bytes. And then these would be 8 bytes. Each of these would be 8 bytes. So the pointer, no matter what, if it's a double pointer, it's going to point to, it's going to be 4 bytes that are used for just holding the pointers to the actual numbers themselves. So when I work with a double, if I want a double array, I would say double here, and then I would put a double pointer here. And this is where I say new double, but this is where the syntax gets kind of squirrely, because when we're creating the first array here, we're creating this guy right here. That actually has to be pointers. The system has got to know that this is 4 bytes. Each of these is 4 bytes. So what you do is you put an asterisk right here. So basically you're saying, give me 3 pointers and assign it to PTR. So now this actually takes care of this portion, you know, creating this top right here. And one also thing that you need to do is you need to delete. But here's kind of the thing. We've created just the pointers. We've got to ask the memory for each one of these guys. So what we got to do is we got to have a loop. And in that loop, we've got to say, okay, pointer of I equals a new double. So this is actually going through each one of these guys right here. It's going through this first one, I of 0, I of 1, I of 2, and it's asking for these 3 doubles. Oh, I got a syntax issue here. This has got to be 3. So we create the pointer array, and then we create the actual numbers to hold the information. And now we can actually fill that information up. So once we create the memory, we can then go in and say, okay, this is going to be for the second, or for each of these guys. So we're going to do J here. We're going to go in and we're going to fill up each of these guys right here with values. We've created the memory form right here on line 12. We're going to actually fill them up with values. So we're going to go here to equal 0. J is less than 3, j plus plus. And then what we'll do is we will say that pointer of I, j is equal to, and it doesn't make sense to use L values here with pointer arithmetic. You know, just create the variables and then use R values where you use your actual subscript. And I'm using those L values, R values, because when you get an error, that particular vocabulary, because when you get an error in the compiler, it refers to L values, R values. You'll see it, and I guarantee you're going to have an error that pops up because we're going to be working a lot with pointers this quarter, especially when we start templating with linked lists, and binary trees. So this is something that you kind of really want to have a good grasp of. So here we're going to be filling up with, let's just say that we'll do I plus j. Just fill it up with a value. So that's actually creating the array for holding the pointers to the actual second dimension here. So this is the first dimension. This is 0, 0, 0, 1, 0, 2, 1, 0, 1, 2, or 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Okay, so we then, once the memory is created for that particular area, the first time that 0 comes in, we create this memory. Then this loop is just to go through each of these and fill it up. Okay, and then what we can do then is we can have a whole nother loop just to print them. And let's say here, this is just printing, so we don't need this. And what we'll do is we'll do a cout of the particular element, and we'll do let's do a space in between. And then after we're done with that, we'll do an end line. So we're going to kind of create a matrix type thing. And here's where then things kind of get dicey, because we've filled the memory, we've printed the memory. Now we need to free up the memory, but you got to do that in reverse order. So we've got to actually take this loop here and just use this first portion, because what you got to do is I'm going to finish this up later, but when you go to free your memory, is you can't free the master pointer first. You cannot free this memory and free up this array, because then that would leave these guys out out there and create a memory leak. So what you got to do is you got to free each of these arrays first. You got to free this one, free this one, free this one, then this one. Then you could free the whole array. So this is going to go through each of them, and we're going to delete each particular array. So I is going to start at 0. So this loop is going to go through and free each of these guys. And then when that's done, we've got to delete the master pointer, which is this guy right here. So you have to free your memory in the reversed order of how you create it. So here we created the master first, and then each of the second dimension pieces. We used the first and second dimensions here. And then we have to reverse, we have to free it in reverse of what we created. So we're going to free each particular portion, and then we free the master double pointer. So that's kind of what a double pointer is. You know, it's kind of interesting, the syntax and semantics that you work with, but a double pointer is just a pointer to a pointer. And this is a simple example of working with it. Let's go ahead and let's see if we get any errors and run this. And then that's going to be pretty much your introduction to this course is pointers. They're important. Learn them and work with them, because we're going to start working with not simple data types. We're going to start putting in user-defined data types. We're going to start working with pointers to objects. Okay, so this guy's ready to run. And there we go. There's our multi-dimension pointer-to-pointer array, created, filled, printed, freed properly. All right, so that's kind of our first little run for the week. Now what I'm going to do next week, it's not going to be a huge lecture next week. The following week will be important because we're going to start doing linked lists. We're going to build one. I'll build one with you. We'll go through every little portion of the linked list, and then we're going to template it when we get to the template chapter. And it's going to be, after a while, that linked list, you're going to start looking at it, and you might get cross-eyed if you don't follow along. But pointers, they're actually stupid simple. The only issue that you have is the syntax and semantics, like this weird thing right there. But if you know what's really going on behind the scenes, and you remember that the 3 sides of pointers, it's really simple. And once you start with a good basis, then after that, it just always boils down to those 3 sides of a pointer. What the pointer points to, the address of the pointer itself, because these guys are, this guy is pointing to the address of this pointer and it's contiguous. And then these pointers point to the address of this guy, it's contiguous. So you've got the address of the pointer, the address of what the pointer points to, and then the value of what the pointer points to. 3 sides of the pointer. Very simple. All right, guys. Thank you.